Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A Level Chemistry Unit 4 for June 2022. This is the part one video of this paper. I will do the paper in 3 videos and I'll put the links to the other videos below in the description box. Let's begin with question 1. Question 1 says this question is about proton NMR spectroscopy. How many peaks are there in the low-resolution proton NMR of 2-methylpropan-2-O? What we have to know here is they're looking for low resolution and it's a proton NMR. So we are looking at the hydrogens and there is no splitting. So I began off by drawing the structure of 2-methylpropan-2-O, which is a tertiary alcohol, as you can see here in blue. And then I observed that this proton here and the protons here, as well as these, they are all in the same environment. So if I call this environment 1, it leaves 1 proton the other side, which is the second environment, and therefore we have only 2 different proton environments in the low resolution proton NMR. Part B says which compound has 3 peaks with a relative area or relative peak areas of 3 to 2 to 1 in its low resolution proton NMR. Again, here I began off by drawing the structures. You can see propanal is like that, propane is that, propan-1O and propan-2O. With propanal, we can see the environments are that, and that. They're all different. And in here we have 3 protons. Here we have 2 protons and that's 1. The smallest ratio is 3 to 2 to 1, which corresponds to the answer we're looking for. However, I went on further to show you how you could find the ratios in the other substance or the other molecules that were given. Propane is like this, and we can see this as well as that they are in the same environment. So we have 6 protons and then 2 protons in another environment. So it gives us a 6 to 2, which is the same as a 3 to 1. So this is in a 3 to 1 ratio. Then propan-1O structure is like this, and we can see it's a 3 to 2 to 2 to 1, and therefore having 4 peaks, that is going to be the ratio for the proton or the area ratio we have. Here we also have propan-2O, which is a secondary alcohol, and this environment, these protons and these protons are in the same environment, as you can see that and that. This is different and that is different. So we have a ratio of 6 to 1 to 1 with the 3 peaks, so that gives us that. And again, to emphasize, remember 1, 2, 3, 3 peaks, 1, 2, 2 peaks. We have a 1, 2, 3, 4. We're going to have 4 peaks here and 1 with that 1, 2, 3. So it gives us 3 peaks. Moving on to the next question, it says which compound does not have a singlet peak in its high resolution proton NMR spectrum? So we're looking for something that doesn't have a singlet peak. And I began again by drawing all the structures. Butanoic acid is like this, and we can see this one here is a singlet. Butanone is like this, and we can see this is a singlet because there is no hydrogen on this carbon atom. Butanol, its structure is like this, and you can see there is no singlet here. While D, which is butan-1O, has a singlet, which is that. So the right answer should be a C. It is only butanol that corresponds to the answer we're looking for. It does not have any singlet in its high resolution proton NMR spectrum. So moving on to question 2, it says the high resolution mass spectrum of an organic compound X has a molecular ion peak with a mass to charge that and another peak with that. Because this is the molecular ion peak, this peak here should be due to fragmentation. So they go on to ask which compound is X. What you could do is go through and find which is required. You could calculate the molecular mass. So I tried. The answer I got, it's only this one that was corresponding to the molecular ion. And of course, in here, we cannot find a peak at 29.0390. And even in here, we cannot find that specific peak. So it was only this one and this one where we could potentially have a peak at that due to fragmentation. And when I calculated the molar mass here, I found 58.078, which is not what we are looking for. We are looking for 58.0417. When I calculated for this one here, I got exactly what we're looking for, so the answer comes out as a B. So this is the answer you're looking for. Going to question 3, it says, a high-performance liquid chromatography HPLC system used a column with a non-polar stationary phase. Remember, if the stationary phase is non-polar, it means the non-polar substances within the compound you're trying to analyze or the mixture of compounds you're trying to analyze will interact with a stationary phase more, and therefore are going to have longer retention times. So they say, and a solvent of methanol as well as water. So this one here is polar. So they say a mixture of octane, octanol, and octan-1-O was placed into the HPLC column. What is the order of the retention times? Remember, the non-polar substance is the one that is a stationary phase. So we expect among these three, the non-polar substance will be retained in longer. Since octane is purely a hydrocarbon, we expect it to last longer, and then octanol, which is slightly having some, it can have some polarity due to the permanent dipole. It could be able to come in next, and then this one here is going to come in the fastest. So number 1, number 2, number 3, and you can see the answer comes out as D. Octan-1-O, which can form intermolecular hydrogen bonds, comes in first. Then octanol can come in next because it has some dipole as well, and octane, which is non-polar, will come in last. So it will have the longest retention time. We are done with question 3. Let's go into question 4. Question 4, a diagram of a thin layer chromatogram of substance Y is shown below. So we assume this is what we have. And then they ask, what is the RF value of substance Y? Now, like I said again, I'm doing this paper using a tablet. So if you're using a real paper, you can use a ruler and measure this distance. So what I got is I can see that this distance here is 3/4 of this whole distance. So if this whole distance is X, that is going to be 3/4 of X. So what I did is to find, remember we are looking for RF, which should be this distance here divided by that distance. So when you divide 3/4 of X divided by X, it gives you a 0.75, which gives us the answer as C. On a paper, you would use a ruler and measure this distance, and then measure that distance, and you would divide this distance by that distance. Then you get the RF value for that specific sample. So that's the answer to question 4. Let's move on to question 5. It says, which reaction cannot form a carboxylic acid? So let's see, the first one says oxidation of a primary alcohol. Primary alcohols can be oxidized to form carboxylic acid, so that it can. Acid hydrolysis of nitriles, these can. When you hydrolyze nitriles under acidic conditions, you can produce a carboxylic acid. And then alkaline hydrolysis of an ester, this produces a carboxylic salt, not a carboxylic acid. So the answer should be a C for question 5. Let's go to question 6. It says, which alcohol could not be formed by the reduction of an aldehyde or a ketone? Remember, when you reduce an aldehyde, you can get a primary alcohol, and when you reduce a ketone, you can get a secondary alcohol. So I wrote all that information down here to an alcohol, which is primary, and that is secondary alcohol. So we are looking for which alcohol could not be formed. So everybody, you can see if this one, it means we cannot form primary, we can form primary and secondary. So A, I drew the structure of A, which is a primary alcohol. We can see B is a secondary alcohol, C is a tertiary alcohol, and D is a primary alcohol. So it means when you reduce an aldehyde, you form a primary alcohol, and a ketone, you form a secondary alcohol. So the only alcohol that couldn't be formed is this tertiary alcohol. So the answer is going to be a C. I drew these structures in order to see which one is primary, which one is secondary, and which one is tertiary. I hope you can follow me on that. Let's go to question 7. It says, what is the pH of a 0.01 mole per decimeter cubed aqueous solution of carbonic acid? Ka is given here, and then at 298 Kelvin. Carbonic acid breaks apart like this because this is, of course, it's a reversible reaction. And from this equation, we can see Ka is going to be the concentration of this times the concentration of that divided by the concentration of this. But I skipped that step, and I assumed the concentration of this is the same as that because that is a fact. So I said it's going to be Ka is equal to the concentration of that squared divided by the concentration of this. And again, remember there are assumptions that are done in this calculation. You assume that the concentration of this initially is exactly the same concentration at equilibrium. Therefore, this is equal to that. So I went on to make H the concentration of hydrogen ions the subject, and it gave me this. So when I substituted in the value for Ka as well as the value for the concentration of the carbonic acid, I got this answer, and I got that. Since I know that pH is equal to the negative log of hydrogen ions, when you find the negative log of that, it gives you a 4.17339, which you round off to get a 4.17, and therefore B ends up being our answer. So moving on to question 8, it says, what is the pH of a 0.27 mole per decimeter cubed aqueous solution of sodium hydroxide? Now remember, this is sodium hydroxide. And again, I wrote the equation for you. Sodium hydroxide is a strong alkali, so it's going to break apart completely, not reversibly like this. It will go completely, producing sodium ions and hydroxide ions. So it means the number of moles of these are going to be exactly the number of moles of these. But since they are in the same volume, it means the concentration of this is going to equal to the concentration of that. Therefore, 0.27, which is the concentration of that, is exactly the concentration of that. Now, since I know that Kw is equal to the concentration of H plus times the concentration of OH minus, I can make this the subject to give me Kw over the concentration of OH minus. Remember, I have this and I have that, so I can be able to find this through this. So I use this, and my calculator gave me that. So this is the concentration of hydrogen ions, and when I find the negative log of that, it gives me a pH of 13.43, which gives me B as the answer to this question. Let's move on to question number 9. Question 9, a 0.1 mole per decimeter cubed aqueous acid solution was added to 25 centimeters cubed of our 0.1 mole per decimeter cubed aqueous solution of an alkali. So let's see, they say the titration curve shown was obtained. So they go on down here to ask which titration would be produced by this curve. If you see, this curve begins from here, so it means this was, of course, it should have been a weak alkali. A strong alkali would be a little bit higher. So this is a weak alkali. And because it ends a little bit lower, we can see this is a strong acid. So this was a titration between a weak alkali and a strong acid. Now, it means among these answers, we have to look for something which falls into that category. So we can see ethanoic acid is a weak acid, so that's out. Hydrochloric acid is a strong acid, but sodium hydroxide is also strong, so that's out. So it means hydrochloric acid and ammonia, which is a weak alkali, so the answer is going to be that. And again, remember, this is ammonia solution, not just ammonia. So the answer should be a D, because it makes sense when you look at the curve or the shape of the curve. Question B says, which indicator will be most suitable for this titration? If you want to know which indicator is most suitable, you have to look at the vertical part of the curve, because the indicator should have a pH range within the vertical part of the curve. So let's see, this is out of the range because this part will be a little bit lower than the vertical region. This is also out. Let's assume, let's see, this is way higher. It's only this that fits. 4.2 to 6.3 is about that range. So the only suitable indicator is going to be methyl red, because the vertical part of the curve and the pH range are kind of in sync. So it makes sense. Let's go to question 10. Question 10 says 4 graphs are shown. So we can see these graphs. Okay. They say which graph shows the rate of reaction on the vertical axis plotted against concentration of a reactant on the horizontal axis for a zero order reaction. What I did, I drew for you this curve from your textbook, you know, the rate versus concentration of a reactant. If it's like this, that is zero order. If it's like that, that is first order. And if it's like this, it can be second order. So since they're asking for a zero order reaction when there is a rate against concentration, it's only this graph that corresponds to that zero order reaction. So the answer should be a C. The next, they say, which graph shows the rate of reaction on the vertical axis plotted against concentration on the horizon of the reactant on the horizontal axis for a first order reaction? Of course, like that. So we will go back to our curve and look for anything that matches that. It's only this graph 4. Therefore, the answer should be graph 4, which is a D. Let's go on to question 11. Question 11 says, propanone reacts with iodine in the presence of sulfuric acid as a catalyst. So they've given us some reaction here, and then they ask which method would be most suitable for the following this reaction. Now, one thing we need to know is this has no color, this is colored, that has no color, and that has no color. So it means we can possibly use colorimetry. However, they also say timing how long the solution takes to go cloudy. In this reaction, nothing is going to go cloudy, so that is out. Another part, they say quenching and titrating with an acid. Acids are going to be titrated if there is a base. In this case, there is no best, so this is also out. Lastly, quenching and titrating with starch solution. No, this is not right, because if you add starch solution to this, everything is going to turn blue-black, and then you will not be able to carry out the titration. So the only perfect thing is going to be colorimetry, because there is going to be a color transition as this color fades away during the titration. So the answer should be an A. And here they say the rate equation for this reaction is here. So they've given us the rate equation, and they ask 2 experiments are carried out, or in both experiments, the concentration of propanol and iodine remain, they say they remain the same, but the concentration of sulfuric acid was changed. Then they're going to ask, the initial rate of the first experiment was 3 times faster than the initial rate of the second experiment. Then they say in the first experiment, the initial pH it was 1.50. What is the pH in the second experiment? One thing we need to know is they said, remember this is the equation, so it means it's first order with respect to both. And if this remained constant, and this is first order, yet they varied this and the rate became 3 times, it means this concentration was multiplied by 3. So here I began by saying the factor multiplied by that will also multiply the rate, since it is first order with respect to H+. So when they say the rate of the first is 3 times the rate of the second, it means the concentration of the first is 3 times the concentration of the second. This is because they are both first order based on the rate equation. So in the first experiment, when they say the initial pH is 1.5, I am going to do that and find the concentration of hydrogen ions in the first experiment, which will be negative log of pH is 1.5, and the hydrogen ions will be 0.031622. So after finding the hydrogen ions in the first experiment, I am going to use that information to find the hydrogen ions in the second experiment. So in the second experiment, the hydrogen ions should be 1/3 times the concentration of hydrogen ions in the first experiment, using these 2 things. So that means it's going to be 1 times 0.031622, giving me that. Let me try to move that so that you can see it clearly. I will move this down here, and then this one down here so that you can see all the number. So finally, when we go down here, we can see pH will be the negative log of that concentration, which ends up being 1.98. So the perfect answer is going to be this. So to get this answer, they must have multiplied it by 3, the concentration of hydrogen ions. This is by 6, and that's the pH by 3. So the only possible answer is a B. Please, I would prefer that you follow my working clearly, because it's easy to understand. Based on the rate, the key thing was you understanding that the rate from the rate equation, each is first order, and then using this information to know that if the concentration is multiplied by a certain factor, since it's first order, the rate multiplies by that same factor, provided the concentration of this one was not changed. That was the only thing you had to know. So let's move on to question 12. Question 12, a series of experiments was carried out to determine the rate constant K of the reaction between bromide 5 ions and bromide ions at different temperatures, T. The graph of natural log K was plotted against 1/T, and the gradient of the line was negative 4670 K. The Arrhenius equation may be written as, they've given you this Arrhenius equation, natural log of K is equal to negative EA over R times 1/T plus the constant. This one is in the form of y is equal to mx plus c. So it means when they ask you to find the gradient, this is going to be the gradient, negative EA over R. So here they say, what is the activation energy of this reaction? Remember, they've given us the gradient as that. That should equal to negative EA over R, giving us that. And therefore, EA should be the value given times R. And since they've given us R here, we just multiply, and I got this. However, how do we get the units? Remember, R is a joule per mole per Kelvin, and then the value given here is K. I had to make sure the units are exactly the same. When you multiply the units, you get this value in joules per mole. So I wrote that in joules per mole. And therefore, the only possible answer was this one, because when you convert it to kilojoules, you get 38.807 kilojoules per mole, which is going to be approximately 38.8. And therefore, the answer should be A. The key thing here was your understanding or knowing that you had to convert the units, or you had to know which units you were working with in order to predict that it had to be kilojoules per mole and not joule per mole per Kelvin or any other units. So question 13 says, solid vanadium 5 oxide catalyzes the equilibrium shown. Here we have that. They ask which statement is correct. Okay, so they say vanadium 5 oxide is a homogeneous catalyst. That is wrong. Remember, they've said it's a solid and these are gases, so it cannot be homogeneous. It is heterogeneous. Part B says decreasing the pressure would increase the equilibrium yield of sulfur dioxide. When pressure is decreased, the equilibrium shifts to the side that has more moles of gas. In this case, if the pressure was decreased, equilibrium will shift, producing more of this, not sulfur trioxide. So that is wrong. And then she says, increasing the surface area of the catalyst would increase the equilibrium yield of that. Increasing surface area only increases the rate, not having an effect on the amount of the product. It has an effect on how fast the product is formed, not how much of the product is yielded. So that is wrong as well. And this says decreasing temperature would increase the yield of sulfur trioxide. This is correct because the forward reaction is exothermic. If you decrease the temperature, equilibrium will shift to the other side, producing more of that. So the answer here should be a D. Question 14 says, in which series does the standard molar entropy of the compound increase? Remember, standard molar entropy is about this order. If it's increasing, we have to make sure heavier, you know this part here, the heavier the molecule, the larger the molar entropy in the same state of matter. So here we can see, looking at these two, we can see these are solids. Solids cannot have a higher entropy than the gases, so these two are already out. So we can consider these two and see calcium oxide is a solid, correct? And then we go to water, that is the liquid. Now the difference is in the gases here. However, when we consider the molar mass, sulfur dioxide and carbon dioxide, of course, we're going to see that sulfur dioxide has a higher molar mass and therefore it qualifies as having the highest molar entropy. Therefore, the correct answer should be an A. Let's move on to question 15. Question 15 says experimental lattice energy values determined using the Born-Haber cycle often differ from the calculated theoretical values. The ionic radii and charges of some ions are shown. P, Q, R, and S are not the chemical symbol of the elements. So they ask, which of these compounds would be expected to show the largest percentage difference between the experimental and the theoretical lattice enthalpy or lattice energy? One thing we need to know is these are all ionic compounds, right? Remember, they can tell us the ionic radius. So let's see, P and R. If you look at this, P is actually, the radius is, it's really small and it's a positive, that is okay. However, R is not the biggest anion. To have the highest difference between experimental and lattice, it means we should have the highest polarizing power or highest polarization or greatest polarization so that we can have the. So basically what we had to do here is to choose the compounds or the ionic compounds that are going to have the highest polarization in order to achieve the greatest difference between difference between theoretical and the experimental lattice energies. So this is the smallest cation and that is the largest anion. So these two, if they come together, we will see it's going to have the greatest difference because of presence of covalent nature of covalent character. So the answer ends up being B because we have the smallest cation, the biggest anion coming closer together, and polarization is going to occur, creating covalent nature or covalency, meaning we're going to have the greatest difference between the experimental as well as the theoretical lattice energies. So the answer for that is a B. This brings us to the end of this part of the video, the first video for this paper. Please do not forget to subscribe. I will put the links below in the description box to the other videos. See you in our next video. Bye-bye.